Our first lab is called a Tumble Buggy lab. And so we're going to use small battery-operated cars that look like this to do an experiment. Our goal is to be able to explain how these tumble buggies move. In order to get started, let me just show you a quick picture of what these look like when they're moving. Let's see here. Go back to here. So they have a switch that you can turn on or off, and then that makes the wheels move. When they run into a wall, they flip over. That's why they're called tumble buggies. Okay, so our goal again is to get some data and try to make a linear mathematical model that will explain the motion of the tumble buggy. Now, we're limited in the type of tools that we have. In our classroom, we're going to be using meter sticks and stopwatches. An alternative to the stopwatch is to use the stopwatch on your phone. Either of those are probably comparable. So our tools are not very sophisticated. Now, we're probably thinking that, when we start thinking, well, what do we want to measure here? And how can we measure it? Well, I would really like to know the speed of the tumble buggy. But the thing is, none of our tools measure speed. All I have are meter sticks and stopwatches. Speed is a value that I could maybe calculate if I knew the distance that the buggy moved in a certain amount of time. And so really, speed is not going to be something that we can measure directly, but we may be able to calculate it if we measure the underlying things that are needed to understand speed. So to know speed, I need to know distance and time. And truth be told, we really don't even have a tool that will measure distance, right? A meter stick can tell me where the buggy is at any point in time, but distance means something else. Distance means how far the buggy has moved away from its starting position. In fact, as a physicist, we would call this displacement. So displacement is the change in position of the object, and it will be represented by the symbol delta x. That Greek symbol delta, the triangle there, it always represents a change in some variable, and x is the symbol that physicists use to represent an object's position. So the displacement is always calculated as the final position minus the initial position. So if I want to find the displacement, I really need to find two different variables, the initial position and also the final position. Now, when we measure position, we're going to be looking at where the buggy is next to a meter stick. And we may use a ruler or some straight line object. Here I've just drawn a red line from the front bumper of the tumble buggy over to where it is passing the meter stick. So that is going to be how we will measure the position of the buggy. And so I'm getting closer to an understanding of what we can measure. So it started out that I really wanted to know the speed, but I realized when I thought about it, that's a calculated measurement, and it really depends on distance and time. Now, time I can measure directly using a stopwatch, but in order to get the distance, I really need to measure two things, the initial position of the buggy and the final position of the buggy. Luckily, both of those positions can be measured with my tool, which is a meter stick. Okay, so the bottom three rows in this table, those are the direct measurements that we'll be taking. Now, the purpose of this lab is to find a model that explains the displacement of the tumble buggy, or how that displacement changes for different amounts of time that the buggy is running. I'm going to let the independent variable be the amount of time that the buggy is running. I can choose that right now. I can decide how I'm going to design this experiment. The time is under my control. The dependent variable, though, is going to be the final position of the buggy. I don't know what that will be until I test it. That final position depends on how much time I let the buggy run. So it is the dependent variable. And if I'm going to have a controlled experiment, the only thing that we're going to change is going to be the amount of time that the buggy runs. Anything else, any other variables must be held constant. And let's just make a list of some of those constants. So first, there are different Tumble buggies in our classroom, and so you always want to use the same Tumble buggy for every trial. And please be sure to record the buggy number that you are using. Also, you want to use the same test setup for every trial. You're going to put your meter sticks down on the floor and take them down. You're going to have the same floor surface. You're going to do everything as identically as you can. And we'll just let the statement of the same test setup summarize that. You always want to begin the buggy at the same initial position. That initial position will be assigned to you just before you begin getting data. Please record that initial position because we need to remember that. And also, because we want to do this experiment as consistently as possible, we want the team members to perform the same jobs throughout the experiment. Those jobs are the person who drives the buggy, the timer who operates the stopwatch, the test engineer who measures the final position, and the quality engineer who makes sure that the team is doing everything, is following the correct process and doing everything consistently. So we want to record the names of the people who are performing each of those roles. Now, remember, we've read about how to make linear models, and one of the principles for good data collection is to prepare a table to store the data before you run the experiment. And for this Tumble Buggy experiment, we want a table something like this. We're going to use 5 different levels of the independent variable, which is time. So we're going to measure how far the buggy, the final position of the buggy after it's been moving for 2 seconds, and 4 seconds, 6 seconds, 8 seconds, and 10 seconds. Now there is some natural variation in every process, and then also we want to make sure that we are getting consistent data. So at each level of that independent variable, we will conduct the experiment for 3 trials. So we'll do the experiment 3 times, and each time we'll record the final position of the buggy. Then, for each level of the independent variable, we'll calculate the average position of the buggy. Okay, so this would be the type of table that you want to use. Now, when it comes to measuring buggy position, we want to measure the point at which the front bumper is aligned with our meter stick. So I wanted to just mention how to read a meter stick. Here's a blown up picture of a portion of a meter stick, and the smallest increment that's labeled on the meter stick is the millimeter. So the tiniest divisions here, each one of those is a millimeter, which is 1/1000th of a meter. And then the numbers that you see on the meter stick are identifying the centimeters. So every 10 millimeters is 1 centimeter. We're going to record our position to the closest millimeter. Let me show an example. So here, this Tumble Buggy has stopped. It is, in the blue line, is showing where it crosses the meter stick. And you can see that the front of the buggy, which is represented by that blue line, is about 6 of those small millimeter positions past the centimeter that's labeled 61. And so we would record this trial as 61.6 centimeters. Okay, once all of the data has been collected and you've calculated the average positions for each level of time that was measured, we want to make a scatter graph of the average final position versus the time that the buggy was running. I have given you a sheet of graph paper, and we're going to make this graph by hand. So you want to turn the paper so that you are viewing the page in landscape mode. In other words, the widest dimension of the graph is going to be the time axis, and the shorter dimension of the page will be the buggy position axis. Be sure to place a good title above the graph and label the horizontal and vertical axes with both the name of the variable and also the units that that variable was measured in. Then you're going to have to figure out the scale for your graph. Now on the time scale, that axis, that scale should be the same for every team, every person. Everyone is using the same levels of independent variable, and so we need to show time going out to 10 seconds. Since there are 50 squares per along this length of the page, if you divide the 10 seconds of data versus the 50 squares, we see that each square is going to represent 0.2 seconds. In other words, every 5 squares is 1 second. And so you want to count over 5 squares and label it 1, count 5 more and label that 2, and so on, going across the graph all the way to 10. Now on the vertical axis, the scale may be different depending on your data. You need to find your largest average position and then divide that by the 37 squares that are along that length of the graph. You probably will get a decimal number, and so you're going to need to round to the most reasonable whole number of centimeters per square. Here is an example of the final scatter graph. This is imaginary data. It does not match any team's particular data, but it does show how the graph should be created. Follow, please, all of the principles that were described in the reading that you did in the previous unit. We want to carefully plot the average position, draw a point protector circle around each data point. Also, be sure to plot the initial position, right? That was the position of the buggy at time 0, and that represents your y-intercept. Then, when all of the points are graphed, use a straight edge to draw a line of best fit that represents the linear trend. Keep in mind that this line of best fit may not go through every single data point. Please do not just connect the dots. You must use a straight edge and draw a straight line that represents your judgment of the best trend. Once you've drawn that line of best fit, you will choose 2 points on that line, not data points. Choose 2 points on that line of best fit that will be used to find the slope. You'll label those 2 points that you chose using a triangular symbol, and above those triangles write the XY coordinates of that point.